My name is Aklant. Oh, sorry. So in the next 5 minutes, I'll be taking the opportunity to briefly introduce to you this new suite of cosmological hydrodynamic simulations called the BRAHMA simulations, which was built with the core objective of learning about black hole seeding from current and next generation observational facilities. So the key feature of our BRAHMA simulations is that basically this novel implementation of black hole seed models for application in cosmic volume simulations. So we have two key distinct suites of simulations that we constructed. One focuses on modeling of lower mass black hole seeds, where the idea is to basically have a series of boxes with successively increasing volumes and decreasing resolutions. And we focus on explicitly resolving these low mass seeds down to 10 to the power 3 solar masses, only in the smallest volume, highest resolution box. And based on how these seeds form in these high resolution boxes and how they grow, we basically built this novel stochastic seed model to seed the descendants of these low mass seeds in larger volume, low resolution simulations without having to explicitly resolve them. And then we have another set of boxes which focuses on heavy seed models, largely motivated from direct collapse black hole formation conditions, where we apply a wide range of seeding criteria based on what we think would contribute to direct collapse: high gas densities, low gas metallicities, high enough Lyman-Miller radiation, low gas spins, as well as rich enough galaxy environments. So in the BRAHMA simulations, our seed formation sites typically are these small, dense metal pore pockets of gas that are existing in these partially metal-enriched halos. So here are a couple of examples of that. The top panel shows an example of a low-mass seed formation site, where you can see for a given region the gas density profile, the star formation rate, and a gas metallicity profile. And this blue circle over there, you can see, is basically an example of a pocket, which is, you can see, is embedded within a much larger metal-enriched cloud. And then for direct collapse seed formation site, we can see similar pockets of dense and metal pore gas, with one key distinction, where around these pockets, the surrounding star-forming regions are providing sufficient Lyman-Miller radiation to suppress the star formation inside these pockets and thereby create conditions for direct collapse black hole formation. So with all of these seeding prescriptions, what we did was conduct a large systematic study to quantify the impact of black hole seeding across a wide range of black hole observables, which I'm about to show you, starting with predictions for merger rates relevant for LISA. So what you see here is a set of seed model predictions for upper limits of black hole merger rates. I say upper limits because we have somewhat optimistic assumptions for the black hole dynamics here. And the plot to the left shows merger rates of 10 to the power 3 solar mass black holes for a set of low mass seed models, where each different color assumes a different assumption for what fraction of dense metal pore gas can be effectively converted to a black hole seed from a pocket. And we can see that the merger rates can range anywhere between 200 to 2,000 potential mergers per year, which is fantastic because even if a small fraction of them end up actually merging within the LISA band, we can still expect several merger events for LISA. And then the right panel shows merger rates of 10 to the power 5 solar mass black holes, where we compare two distinct scenarios, one where these black holes directly formed as heavy seeds, and other where these black holes are descendants of lower mass seeds. And we can see how these heavy seed models tend to categorically produce much higher merger rates compared to lower mass seed models, particularly when we focus on redshifts greater than 15 or so. Here are predictions for stellar mass versus black hole mass relations for a set of heavy seed models at high redshifts, and compared against the JWST measurements of overmassive black holes. And you can see if you focus on the more optimistic seed models, for example, the leftmost seed model is perhaps too optimistic, where we assume that for every dense metal pore pocket of gas, we form a heavy seed. These models tend to more readily produce these overmassive black holes, whereas once we make the model more restrictive by adding Lyman-Miller flux criterion, low gas spin criterion, or rich environment criterion going from left to right, the simulations start to struggle to reproduce these overmassive black hole populations. And then finally, here I'm showing predictions for the local black hole occupation fractions in dwarf galaxies. And here again, you can see substantial variations of occupation fractions of greater than 10 to the power 5 solar mass black holes in these dwarf galaxies. Of course, current observational constraints are too uncertain to be able to strongly rule out any of these seeding scenarios, but we hope that in the future we'll have lesser uncertainties in the inferred occupation fractions, and then we will be able to rule out some of these seed models using local observations as well. And with that, thank you very much.